We've always imagined threats from space arriving with warning sirens blaring, with years of preparation, with humanity united in vigilance. We've built billion-dollar detection systems, positioned telescopes across continents, and trained our best minds to scan the cosmic darkness for danger approaching Earth. We tell ourselves we're watching. We tell ourselves we're ready. But on October 1st, 2025, at exactly 8:47 p.m. Eastern Time, something passed closer to Earth than the International Space Station, closer than weather satellites, closer than GPS networks that guide every plane in our skies. An asteroid measuring up to 10 feet across screamed over Antarctica at 428 kilometers altitude, moving at thousands of miles per hour, and we didn't see it coming. Not until hours after it had already passed. Hours after it had threaded the needle through our orbital infrastructure, missing satellites by mere kilometers. The Catalina Sky Survey in Arizona found it in the rearview mirror of cosmic history. This is Asteroid 2025 TF, and the fact that it surprised us reveals something far more unsettling than the rock itself. The detection came like a ghost story told in reverse. On the morning of October 1st, 2025, astronomers at the Catalina Sky Survey, a NASA-funded mission operated by the University of Arizona, were conducting routine observations of the night sky. They were searching for near-Earth objects, as they do every clear night, scanning telescope data for anything unusual moving against the background stars. Then they found it, a faint streak of light in images captured hours earlier. When they calculated its trajectory backward through time, the realization hit like ice water. This object had already passed Earth, not in a few days, not tomorrow, already. The European Space Agency's Planetary Defense Office immediately mobilized. Within hours, astronomers at the Las Cumbres Observatory in Australia swung their telescopes toward the rapidly departing object. Tracking a meter-scale asteroid smaller than a car, billions of kilometers into space after its position has already shifted is like trying to find a single grain of sand thrown into the ocean after watching someone toss it. You know it's there. You just have to calculate exactly where. The observations were successful. The data confirmed what no one wanted to believe. 2025 TF had passed just 428 kilometers above Antarctica's frozen landscape. For reference, the International Space Station orbits between 370 and 460 kilometers. Commercial satellites in low Earth orbit range from 160 to 2,000 kilometers altitude. This object flew through our satellite infrastructure like a bullet through a crowd, and we only noticed the sonic boom after it was gone. The asteroid measured between 1 and 3 meters in diameter, roughly the size of a small car or a giraffe standing on its hind legs. Small enough to burn up if it hit atmosphere, but large enough to survive as fragments, scattering meteorites across the surface. Large enough to destroy a satellite if trajectories aligned wrong. But size isn't what makes this story disturbing. It's the invisibility. We have spent decades building the most sophisticated detection network in human history. NASA's Center for Near-Earth Object Studies tracks over 34,000 objects. The Catalina Sky Survey alone discovers hundreds of near-Earth asteroids every year. ATLAS, the Asteroid Terrestrial Impact Last Alert System, operates 4 telescopes scanning the entire sky twice per night, specifically to find threats approaching from any direction. 2025 TF should have been detected days before arrival. It should have triggered automatic alerts. It should have been on every astronomer's watch list as it approached. Instead, it arrived unannounced, passed within satellite altitude, and departed into deep space before a single human being on Earth knew it existed. This is the cosmic equivalent of a stranger walking through your living room while you're watching television and only noticing them when you review security footage the next morning. How does that happen? How does an object moving at orbital velocity, fast enough to cross the United States in less than 90 seconds, simply appear? Most near-Earth asteroids approach from predictable directions. They follow orbital paths that bring them in at angles we can see coming, angles where sunlight illuminates them against the darkness of space, making them visible to ground-based telescopes weeks or months in advance. 2025 TF likely approached from a direction that kept it hidden in Earth's optical blind spot. Asteroids coming from the direction of the Sun are notoriously difficult to detect because telescopes can't observe close to solar glare without being overwhelmed. It's like trying to spot a firefly hovering next to a stadium floodlight. Even our best detection systems have gaps, and this asteroid found one. Objects smaller than 25 meters are extraordinarily difficult to detect until they're very close to Earth. 2025 TF at just 1 to 3 meters is below the size threshold where automated detection systems reliably flag objects weeks in advance. Think of it this way. A 1-meter asteroid is essentially a boulder floating in space. Ground-based telescopes are trying to spot a dark boulder against the infinite blackness of the cosmos, millions of kilometers away, moving at 60,000 kilometers per hour relative to Earth. NASA's NEO Surveyor mission, a space telescope specifically designed to find dark asteroids using infrared detection, won't launch until late 2027. Until then, we're hunting with visible light, and dark objects remain nearly invisible until they're on our doorstep. 2025 TF was dark. It was small. It was approaching from an unfavorable angle, the perfect storm of invisibility. Even after 2025 TF passed, it took hours to find it in telescope data. The Catalina Sky Survey captured it approximately 2 hours after closest approach, but astronomers didn't recognize what they were looking at immediately. Near-Earth object detection relies on comparing images taken minutes or hours apart, looking for objects that move between frames. But with 2025 TF already retreating rapidly after its flyby, its motion was faster than expected for typical asteroid surveys. It was behaving like something that had just performed a gravitational slingshot around Earth, because that's exactly what it did. The orbital mechanics were unusual enough that initial automated systems may have filtered it out as noise or satellite glare. Only when human eyes reviewed the data did the realization crystallize. This was a natural object, not space junk, and it had already passed closer than most satellites. Here's where the story becomes genuinely unsettling. 2025 TF is the second closest non-impacting asteroid ever recorded. The closest was 2020 VT4, which passed just 370 kilometers above the Pacific Ocean in November 2020, also detected only after it had already passed. 2 asteroids within satellite altitude in less than 5 years, both discovered post-flyby. Statistically, astronomers estimate that objects in the 1 to 10 meter size range pass within the Moon's orbit, about 384,000 kilometers, several times per month. But how many pass closer? How many threads through our orbital infrastructure undetected? We don't know, because we can't see them until they're already here. Astronomers estimate that we've cataloged only about 1% of near-Earth asteroids smaller than 25 meters. That means 99% of city block-sized objects capable of causing regional devastation remain completely unknown, and 2025 TF just demonstrated why. If a 3-meter asteroid can pass through the altitude of our communication satellites, our weather monitoring systems, our GPS networks without anyone noticing until after the fact, what else is passing through? What else have we missed? The problem isn't that astronomers aren't looking. The problem is the fundamental physics of detection. Ground-based telescopes detect asteroids through reflected sunlight. An object must be illuminated by the sun and positioned where that reflected light can reach Earth-based observers without being drowned out by atmospheric interference, light pollution, or solar glare. Small asteroids have very low albedo. They reflect only 3% to 20% of sunlight, making them inherently dim. A 1-meter asteroid at 1 million kilometers distance has an apparent magnitude fainter than most telescopes can detect in a single exposure. To find them, surveys must take multiple images over time and compare them looking for motion. But here's the catch. If an asteroid approaches on a trajectory that keeps it in Earth's blind spots near the sun during approach, or moving so fast during close passes that it appears in only a handful of frames, it can slip through undetected. 2025 TF did exactly that. The Catalina Sky Survey operates a 1.5-meter telescope at Mount Lemmon, Arizona, and a 0.7-meter telescope at Mount Bigelow. These are among the most productive asteroid hunting instruments on Earth, discovering hundreds of near-Earth objects annually. Yet even they couldn't catch 2025 TF before arrival. After discovery, the ESA's Planetary Defense Office used the Las Cumbres Observatory Global Telescope Network to pin down the asteroid's orbit with extraordinary precision. They calculated the closest approach time accurate to within 18 seconds. An impressive feat considering the object was already millions of kilometers away and moving at interplanetary velocity. But precision after the fact doesn't change reality. We weren't prepared. We didn't know. Low Earth orbit is crowded. Approximately 11,000 active satellites orbit Earth, with tens of thousands of pieces of tracked space debris. Companies like SpaceX's Starlink are launching thousands more satellites every year. 2025 TF passed through this orbital shell at 428 kilometers altitude. If its trajectory had been slightly different, if it had arrived minutes earlier or later, it could have collided with operational satellites. At orbital velocities, a 1-meter asteroid carries the kinetic energy of several tons of TNT. A direct impact would vaporize a satellite instantly, creating a debris field of high-velocity fragments that could trigger a cascade of secondary collisions, a scenario known as Kessler syndrome, where orbital debris multiplies exponentially until entire altitude bands become unusable. We got lucky this time. Imagine holding a baseball. Now imagine throwing that baseball at 60,000 kilometers per hour, fast enough to circle the equator in less than 40 minutes. That baseball carries enough kinetic energy to level a city block. 2025 TF was larger than a baseball. It was the size of a car, and it passed closer to you than most satellites you depend on every single day. The GPS guiding your phone, the weather satellites predicting storms, the communication networks streaming this video. It threaded between them like a bullet through raindrops, and we only noticed when someone looked at the data hours later. 2025 TF is not an isolated incident. It's a symptom of a larger vulnerability in planetary defense. In February 2023, asteroid 2023 CX-1, approximately 1 meter wide, was detected just 7 hours before impacting Earth's atmosphere over Normandy, France. It became only the 7th asteroid in history successfully detected before impact. 7. In all of human history, we've managed to spot 7 small asteroids before they arrived. The rest? Surprises, post-impact discoveries, objects found in meteor camera footage after they've already burned up an atmosphere. The 2013 Chelyabinsk meteor in Russia, a 20-meter asteroid that exploded with the force of 30 Hiroshima bombs, injuring over 1,500 people, was completely undetected before arrival. It approached from the direction of the sun, and no telescope saw it coming. Between September 23rd and September 28th, 2025, 10 asteroids passed Earth closer than the Moon's orbit. We tracked those because they were large enough and approached from favorable angles. But how many others passed that we didn't track? How many 2025 TF-sized objects threaded through our orbital infrastructure during that same week? NASA's NEO Surveyor mission promises to change this when it launches in late 2027. Operating from space with infrared detectors, it will find asteroids regardless of their approach angle relative to the sun. It will catalog dark objects that visible light telescopes miss. It will provide years of warning for larger threats, but until then, we're vulnerable. And 2025 TF just proved it. Most planetary defense experts will tell us that small asteroids like 2025 TF aren't true threats. They'll point out correctly that objects this size burn up in atmosphere, producing spectacular fireballs, but rarely causing ground damage. But a growing number of aerospace engineers and satellite operators are asking different questions. They're not worried about ground impact. They're worried about orbital impact. As one satellite tracking expert noted in a recent briefing, we've spent billions building orbital infrastructure that civilization now depends on, and we're threading undetected asteroids through it at satellite altitude multiple times per year. It's not a question of if we lose a critical satellite to an undetected impactor, it's when. The debris field from such a collision could cascade. Satellites destroyed, communication networks disrupted, GPS navigation offline, weather forecasting blinded, and the asteroid that causes it, we might not see it coming until it's already done the damage. Asteroid 2025 TF is now departing into deep space, following an orbit that won't bring it back to Earth's vicinity until April 2087, 62 years from now. By then, our detection capabilities will presumably be far more advanced. But the question isn't about this specific asteroid. It's about the next one and the one after that. On October 2nd, 2025, just one day after 2025 TF, another asteroid designated 2025 TQ2 passed over Canada at 4,851 kilometers altitude. This one was detected by the Mount Lemmon Observatory in Arizona and tracked successfully. But at 3,014 miles from Earth's surface, it was much farther away, much easier to spot. The close ones remain invisible. NASA's Jet Propulsion Laboratory maintains a constantly updated database of near-Earth objects and their trajectories. As of October 2025, over 34,000 objects are cataloged. But that catalog is heavily biased toward larger objects, asteroids hundreds of meters or kilometers across that pose civilization-ending threats. Objects in the 1 to 25 meter range, the ones that could destroy satellites, level city blocks, or cause regional disasters, remain largely unknown. The Atlas survey system is designed to provide at least one day's warning for asteroid impacts, giving authorities time to evacuate affected areas. But Atlas, like all ground-based systems, has the same fundamental limitations. It can't see small, dark objects approaching from unfavorable angles until they're nearly here. What we need is comprehensive space-based detection, infrared sensors positioned where they can observe the entire sky continuously, without atmospheric interference or solar glare limitations. We're building that capability, but it's still 2 years away from launch. Every day that passes without comprehensive asteroid detection is another day we're vulnerable. Another day when something like 2025 TF or larger could arrive without warning. The window to detect these objects closes the moment they pass. Once an asteroid flies by Earth and departs into deep space, tracking it becomes exponentially harder. Its distance increases, its apparent brightness drops, and it vanishes back into the cosmic darkness. We have one chance to see them coming. If we miss that chance, we learn about them only in hindsight, if we learn about them at all. This is the window, right now. The years between recognizing the vulnerability and fixing it, between knowing we have a detection gap and deploying the technology to close it. 2025 TF slipped through that gap. The next one might not be so small or so harmless. Planetary defense isn't about paranoia, it's about mathematics and statistics. We know asteroids exist. We know they cross Earth's orbit. We know that throughout geological history, impacts have shaped our planet's evolution and driven mass extinctions. The dinosaurs learned this lesson 66 million years ago when a 10-kilometer asteroid struck the Yucatan Peninsula. But impacts aren't just ancient history. In 1908, a 60-meter asteroid or comet exploded over Tunguska, Siberia, flattening 2,000 square kilometers of forest with the force of 15 megatons of TNT. If it had arrived 4 hours later, Earth's rotation would have placed St. Petersburg directly beneath the explosion. In 2013, Chelyabinsk demonstrated that even 20-meter objects can cause widespread damage and injuries. The explosion shattered windows across 6 cities, sent a shockwave that circled Earth twice, and released more energy than 30 nuclear weapons, and we didn't see it coming. 2025 TF was smaller, too small to cause that level of damage, but it passed closer than any asteroid in 5 years, closer than satellites, closer than the ISS. It's a warning shot, a reminder that our detection network, while impressive, has holes, and something dangerous could slip through those holes at any moment. Modern civilization runs on satellites. GPS navigation guides planes, ships, emergency vehicles. Communication satellites relay internet traffic, phone calls, financial transactions. Weather satellites provide hurricane warnings, track wildfires, monitor climate change. Scientific satellites observe Earth's environment, helping us understand our changing planet. All of this infrastructure orbits in the same altitude bands where 2025 TF passed. Losing a single critical satellite to an undetected asteroid impact could disrupt global systems. Losing multiple satellites in a debris cascade could cripple entire sectors of the economy and endanger lives through lost emergency communication capability. This is the hidden vulnerability that 2025 TF exposed. Not that asteroids can hit Earth, we've always known that, but that asteroids can hit our orbital infrastructure without warning, and we might not realize what happened until services go dark. Right now, radar tracking stations and Space Force sensors are reviewing data from October 1st, checking for any additional objects that might have passed unnoticed. They're examining orbital perturbations of satellites, looking for gravitational anomalies that might indicate close asteroid passes. The data exists somewhere in terabytes of telescope images, radar pings, and satellite telemetry. There are answers. There may be other objects we missed, other close passes we haven't yet recognized. The silence between discovery and revelation, sometimes that silence is the loudest sound in astronomy. What else is hiding in that data? What else passed through while we weren't watching carefully enough? The asteroid detection community is divided not on whether the threat is real, but on how urgently we need to address it. Many planetary scientists emphasize that large civilization-threatening asteroids are well cataloged. NASA has identified over 95% of near-Earth asteroids larger than 1 kilometer, the size that could cause global catastrophe. None of them pose an imminent threat. They argue that smaller asteroids like 2025 TF, while frequent, are not existential dangers. Most burn up harmlessly. Regional damage is possible but rare. The statistical risk to any individual person is vanishingly small, far lower than risks we accept daily like automobile accidents or severe weather. From this perspective, 2025 TF is interesting scientifically but not alarming. It's a reminder to keep improving detection systems but not evidence of imminent danger. A growing number of aerospace engineers and satellite operators take a different stance. They point out that while small asteroids may not threaten ground populations directly, they pose significant risks to orbital infrastructure that modern civilization depends on. The concern isn't about asteroid impacts causing casualties. It's about asteroid impacts causing cascading satellite failures that disrupt critical services. Communication blackouts, navigation system failures, weather forecasting blind spots, military surveillance disruptions. One analysis estimated that losing certain keystone satellites could cost the global economy tens of billions of dollars and endanger lives through lost emergency services capability. From this perspective, 2025 TF is a genuine warning. Not about impacts on the ground, but about impacts in orbit, where we're even less prepared and where consequences could be far-reaching. Both camps agree on the path forward: better detection. Space-based infrared telescopes like NEO Surveyor will find asteroids regardless of their position relative to the Sun. Operating from orbits beyond Earth, they'll detect thermal emissions from asteroids heated by sunlight, making even dark objects visible. Enhanced ground-based surveys with larger telescopes and faster processing can reduce detection gaps. Projects like the Vera C. Rubin Observatory, scheduled to begin operations soon, will survey the entire visible sky every few nights, dramatically increasing the catalog of known small asteroids. Automated satellite collision avoidance systems can be programmed to respond to asteroid warnings, maneuvering spacecraft out of predicted impact zones if sufficient warning time exists. But all of these solutions require funding, political will, and time to implement. And while we're building those capabilities, the asteroids keep coming. Detection systems aren't perfect. They never can be. We're scanning infinite space with finite resources, searching for dark objects moving at incomprehensible speeds. It's like trying to protect a house by watching for mosquitoes, except the mosquitoes are invisible. The house is the size of a continent, and instead of buzzing, the mosquitoes are silent and moving at 60,000 kilometers per hour. Some will get through. 2025 TF got through. The question is whether we'll be ready when one gets through that matters. When the object isn't 3 meters but 30 meters. When it's not passing safely but on a collision course. When we have not hours but minutes to react. That's the scenario that keeps planetary defense experts awake at night. For billions of years, asteroids have carved their paths through the solar system, governed by gravity and momentum, utterly indifferent to the civilizations that might lie in their paths. They are messengers from the ancient past, remnants of planetary formation, time capsules containing the primordial material that built worlds. We study them as keys to understanding our origins, but they also hold the power to determine our future. On October 1st, 2025, one of those messengers passed closer to Earth than the space station where astronauts orbit. It arrived unannounced, threading through our satellites, crossing paths with the infrastructure that powers modern life. It could have collided with a satellite. It could have created a debris field. It could have disrupted systems we depend on daily. It didn't. We got lucky. But luck is not a strategy. Luck eventually runs out. The universe doesn't send warnings before it sends consequences. Asteroids don't announce their arrival. Space is vast, dark, and full of objects moving at speeds that turn even small rocks into weapons capable of massive destruction. We are building the tools to see them coming. We are developing the capability to track every object that crosses Earth's orbit. We are working toward a future where surprises like 2025 TF become impossible, where comprehensive monitoring gives us years of warning for any potential threat. But we're not there yet. And until we are, every clear night brings the possibility of another 2025 TF. Another object we didn't see, another reminder of our vulnerability. The cosmos is beautiful, it's also dangerous. And the thin blue line between Earth and the infinite dark above is more fragile than we'd like to admit. We caught 2025 TF in the rearview mirror, detected it hours after it passed, calculated its trajectory in hindsight. Next time, we might not be looking in the right direction. Next time, it might not be small enough to burn up harmlessly. Next time, we might learn about it only when satellites go dark and systems fail. Or next time, we might see it coming, with enough warning to prepare, with enough time to act. That's the future we're building, a future where space surprises become scientific opportunities rather than existential threats, where asteroids are cataloged years before they arrive, their trajectories known with precision, their potential impacts prevented through deflection missions if necessary. But that future isn't here yet. For now, we watch the skies. We improve our detection networks. We catalog what we can find and acknowledge what we might be missing. We continue the patient work of planetary defense, the unglamorous but essential task of making sure we see the next one coming before it arrives, because somewhere out there, in the vast darkness between worlds, the next asteroid is already on its way, following its ancient orbit, indifferent to our civilization, governed only by physics. The question is whether we'll see it in time. 2025 TF passed closer than satellites, and we didn't know until it was gone. What will we miss next? And will we be ready when we finally notice?